What's up, guys? Welcome back to another Algebra 2 instruction lesson here as we continue our work with exponential and logarithmic applications. Today we're going to take a step into the world of finance and work with equations and situations involving compound interest. So compound interest is when you take out, let's say you take out a loan and you accrue interest on that initial loan that has been taken out. But then also as you accrue interest, you get more interest on top of the interest already developed. That's what compound interest is, and it can work through investment accounts, it can work through loans, but essentially the interest that is accumulating in the account is then applied into the additional interest, as opposed to interest that is applied only to the principal, which is generally a more simple interest formula we have seen before. So we have this equation here for compound interest, and this equation is where P is the initial amount, or in the financial world what we call the principal. R is the rate, as we have seen. T is the time, as we have seen. And now we have this term N. N is the number of times that the interest is going to be compounded. And so we'll just label that as the number of compounds. Not a great way of saying it, but that's what N represents, the number of times that the interest excuse me, is going to be compounded. So in problem number 9, it says an initial deposit of $1,000 is made into an account paying 6% compounded yearly. What will be the account, or what will be the value of the account after 5 years? And how long will it take for the money to double? So in this case, we're going to deposit $1,000, and we want to identify two different things about the account. So when we take a look at the account balance here, the first question is to find the value of the account over time. And in this instance, for let's say the first part of this question, we want to find the amount after 5 years. So we know that our time is going to be 5 years. We also know that the principal is $1,000, so we're going to, that initial amount is 1,000. So in this case, N is going to be 1. So this is the number of compounds. Let me expand on this and call this per period, the number of times that the interest is applied in a period. Unless otherwise noted, the period is generally a year. So the number of times that this is going to be compounded in a year would be once. The interest is going to be compounded only once. So this actually follows into an equation similar to what we've seen before, where we're going to have R over 1, or 0.06 over 1. Remember, the rate is R is the rate, which is 6%, that needs to be converted into a decimal, and N is 1 because it's compounded once during the year. So then our exponent would be 1 times T, which is time, and in this scenario is going to be 5. And so we can evaluate all of this in the calculator. So 1,000 times 1 plus 0.06 over 1, which would be 1.06 to the 5th power. So when it's compounded yearly, this is very similar to our exponential percentage growth equation that we saw previously. So the balance of this, so the approximate balance, we'll go ahead and round to the nearest dollar, or so to the nearest cent. So this would be approximately $1,338.23 value after 5 years. Now the second part of the question asks us to find out how long it would take for the money to double. So in this case, we know that we initially put in $1,000. We want the account to reach double the amount. So we want the amount after time to be $2,000. So 2,000 is equal to 1,000, my principal, times 1 plus R over N, so 1.06. That part is not going to change. But this time we're trying to solve for T, so this would be to the 1T power. And we can solve this equation either graphically or algebraically. I'm going to do this algebraically because it's pretty quick here. Divide by 1,000. So I'd get 2 equals 1.06 to the t power. And then we realize this is an exponential equation. So to eliminate an exponential equation, we need to use the inverse, which would be a logarithm with base 1.06. And that would give us t out of the exponent. So if I want to input this into my calculator, I can quickly use the change of base formula and get an estimation here. And we'll approximate this to the second, to the hundredths place. So this would be approximately 11.89, would round up to 90 years for the account to double. So here we see interest compounded yearly, once during the given period. What if that number changes? So let's take a look at problem number 10, where we're actually going to have a variety of scenarios here. It says Macklin won $150,000 in the Missouri lottery and decides to invest the money for retirement in 20 years. Of all the options available here, which one will produce the most money for retirement? So what we want to do is we want to take a look at the different options, and find the value after 20 years. So we want to find A of 20 for each of these scenarios. So in scenario 1, we have A of 20. It's a certificate of deposit paying 5.4% compounded yearly. So in each of these cases, we are going to have the same principle. We're going to assume she's investing all of the money for retirement. We're going to have the same time period, in 20 years. But what's going to change is how the interest rate is accounted for. So if we look through these options, you might think, oh, 5.4% interest. That's going to be the best after 20 years. But we have to take into account the number of times that it's being compounded. So in A, we are going to be compounded once per year. So as we substitute into the formula, our rate is, put the rate down wrong here. Our rate is 5.4%, which is 0.054. N would be 1, and T would be 20. So we can go ahead and substitute these values into the calculator. So 150,000 times 1.054 to the 20th power. And we can see that after 20 years, our certificate of deposit would be worth roughly $429,440.97. Now let's take a look at some other options that we could have here. So in B, we have a money market certificate paying 5.35% compounded semi-annually. So a lower rate, but compounded more frequently. The interest is being taken more frequently. So if I substitute into the formula this time, my principal stays the same, my time domain stays the same. This time my rate is 0.0535 when I take my percentage and convert it to a decimal. N is 2. If it's compounded semi-annually, it's going to be compounded twice during the year. So N is going to be 2. So I'm going to take this same equation, and now with the changes to the number of times that it's compounded per year, I'm going to insert these new values for the variables and then calculate the account value would be approximately $431,200.96 after the 20 years. So we can see that the second option is already better than our first option. And that happened because though the rate was lower, it was compounded semi-annually, which eventually led to a larger account balance. Let's go ahead and take a look at C. So again, we see the rate decreasing, but we see the compounds increasing. This is going to compound quarterly. So let's see what happens to the account balance over 20 years in this investment vessel. So in this case, if it's compounded quarterly, N is going to be 4. Quarterly would mean that it's going to compound 4 times during the year. T remains 20, P remains 150,000, and now our rate is 0.0525, 5.25%. So I'm going to go ahead and head to the calculator and input these values. Let the calculator do all of this work for me. So 1 plus 0.0525 divided by 4 to the 4 times 20th power, which would be the 80th power. And we would see that this one is compounded more frequently, but the lower interest rate does not add up to quite the amount that the previous two options were. So this would run to approximately $525,729.58 after the 20 years. So far, B, the money market account, is the best option. Let's see if you can pause the video and figure out if D is going to provide a better option. So hopefully you've taken a look at D at this point. We notice again that the principal stays the same. The time domain stays the same. What has changed is our interest rate is now 5.2% compounded daily. So N is now 365 and our rate is 0.052. And as I input that value into the calculator, I get the total account value of $424,351.12. So out of these, which would be the best total offering? The investment into the money market certificate. So we can see that the number of compounds, when that adjusts and the interest rate adjusts, it can make different outcomes for the total account value over the same period. So here we have examples of regular compound interest in the equation that we use to find a value. As always, thank you guys for tuning in, and I'll see you soon.